When people first hear about threat modeling, they often imagine it as a brainstorming session where a team lists scary things that could happen and then moves on. That kind of vague exercise might feel busy, but it does not reliably change the design of a system, and it does not reliably reduce risk. The goal here is much more practical. Take a structured way of thinking about threats and turn it into design decisions that actually prevent, detect, or limit damage. Stride is one of the most widely taught ways to do this because it gives you a simple set of categories that keep you from forgetting important classes of problems. If you can move from the stride concept to concrete mitigations, you can explain why a design includes certain controls, and you can show how those controls map to specific threat types. By the end of this episode, you should be able to look at a system, identify the kinds of threats Stride points to, and then describe what an architecture would do to address them in a way that is testable and defensible. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. STRIDE is an acronym that stands for 6 threat categories: spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. The first time we mention it, we expand it as STRIDE, STRIDE, and after that we will keep it in that spaced form. The value of STRIDE, STRIDE, is not that it magically discovers every possible attack, but that it forces you to consider different ways a system can be harmed. Each category is like a lens you can hold up to a part of the system to ask a focused question. Spoofing is about pretending to be someone or something else, and it pushes you towards strong identity and authentication. Tampering is about unauthorized changes to data or code, and it drives integrity protections. Repudiation is about someone denying an action, which pushes you toward reliable logging and evidence. Information disclosure is about data exposure. Denial of service is about availability being disrupted, and elevation of privilege is about gaining more power than intended. As we move forward, keep in mind that the real work is not naming the category, but choosing mitigations that make the category less likely or less damaging. To operationalize STRIDE, STRIDE, you need a system view that is simple enough to reason about, but detailed enough to be useful. A common beginner mistake is trying to threat model the entire environment in one giant diagram, which becomes so messy that you cannot confidently identify threats. Instead, you want to define the scope of what you are modeling, such as a single application and the services it depends on, or a single business workflow like user signs in and requests a report. In threat modeling, it helps to identify key components like users, processes, data stores, and data flows between them, because threats often appear at boundaries and transitions. Think of data flows as the roads between places and boundaries as the points where the rules may change, such as moving from a user's device to a web server or from a web server to a database. Those boundaries are where identity, authorization, and validation often fail if they are not designed carefully. Once you have this scoped view, you can apply STRIDE, STRIDE, category by category to each important element and connection. The first category, spoofing, becomes practical when you treat identity as an architectural dependency instead of an app feature. Spoofing happens when an attacker can successfully pretend to be a valid user, a valid service, or a valid device, and the system accepts that claim. The mitigation choices here start with how identity is established and verified, which includes authentication strength and how credentials are handled. Strong authentication might mean multi-factor authentication, but the deeper architectural decision is how and where authentication happens and how trust is shared across components. For example, if one service accepts identity claims from another service, you need a reliable way to validate those claims, not just accept a username in a request. Practical mitigations for spoofing include using cryptographically protected tokens for identity assertions, ensuring secrets are not embedded in code, and enforcing mutual authentication between services when appropriate. The concrete output of the threat model is a requirement like service-to-service requests must be authenticated and bound to a validated service identity, which then drives design patterns and security controls. Tampering becomes concrete when you clearly define what integrity means for the system's most important data and code paths. Tampering is not just someone changing a database record. It can include altering messages in transit, modifying configuration, or manipulating a workflow so it does something unintended. The architectural question is where data can be changed, who is allowed to change it, and how you detect or prevent unauthorized changes. Mitigations can include validation at trust boundaries, integrity checks like hashes or signatures for sensitive artifacts, and protections that reduce the chance of unauthorized modification, such as least privilege on write access. Another practical mitigation is designing systems so that high-risk operations require additional checks, such as verifying the state of an object before applying an update. If you only think about tampering in the abstract, you miss the reality that many tampering paths are enabled by design shortcuts, like trusting client-supplied data too much. The threat model should produce specific requirements like critical configuration changes must be controlled, authorized, and integrity protected, and then the architecture must implement a change control and verification approach that matches that need. Repudiation sounds abstract at first, but it becomes very real when you consider how systems prove what happened when something goes wrong. Repudiation is when someone can deny that they performed an action, and the system cannot reliably prove otherwise, which is especially important for financial actions, sensitive data access, or administrative changes. Many beginners think logging is just about collecting events, but repudiation mitigation is about making logs useful as evidence. That means logs must be complete for important actions, tied to reliable identities, protected from tampering, and time-aligned so you can reconstruct sequences. It also means you must decide what events matter and ensure they are captured consistently across components, not just in one part of the system. A strong architectural mitigation includes defining audit trails that link a user's authenticated identity to actions taken, including key context like what was changed and from where. The deliverable from Stride, STRIDE, here is not enable logging, but a requirement like security-relevant actions must be auditable with integrity-protected logs and sufficient context to support investigations. Information disclosure is often the category that causes the most design changes because it forces you to think carefully about where data lives and where it travels. It includes exposure of data at rest, data in transit, and data in use. And it also includes unintended disclosures like error messages that reveal internal details. Architectural mitigations start with data classification at a simple level, such as identifying what data is sensitive, what data is regulated, and what data is public. Once you know which data matters most, you can decide where encryption is required, where access controls must be strict, and where you must minimize exposure by design. Examples of concrete mitigations include encrypting sensitive data in storage, using secure transport for data flows that cross untrusted networks, and limiting data returned to clients to only what is necessary. Another key mitigation is designing segmentation and isolation so that a compromise of one component does not automatically expose everything. A threat model that operationalizes Stride, STRIDE, would turn information disclosure risk into statements like sensitive data must not traverse untrusted boundaries without encryption and must be accessible only through authorized service interfaces. Denial of service can be misunderstood as something only large internet companies worry about, but availability is a security property for many systems, including internal systems that support critical business processes. Denial of service includes intentional overload, resource exhaustion, and exploiting weaknesses that cause crashes or deadlocks. The architectural challenge is that availability depends on capacity planning and resilience, not just security features, so mitigations are often about design patterns that degrade gracefully. Concrete mitigations include rate limiting, back pressure mechanisms, timeouts, and circuit breakers that prevent one failing dependency from taking down an entire service chain. Another mitigation is designing for redundancy and failover so that a single point of failure does not stop the system. You also want to consider how the system behaves under stress, because some systems fail in ways that expose data or bypass controls when overloaded, which is a subtle and dangerous interaction. The threat model should produce actionable requirements like external-facing interfaces must resist request flooding through throttling and resource limits, which directly influences gateway design and service behavior. Elevation of privilege is where you focus on how attackers might gain more permissions than intended, and it often reveals hidden trust assumptions in architectures. This threat category is about crossing from a lower privilege context to a higher privilege one, such as a user becoming an administrator or a service being able to perform actions outside its intended scope. Practical mitigations begin with least privilege, which means each identity, whether human or service, gets only the permissions needed for its role. But operationalizing it requires you to define roles and permissions clearly, decide where authorization decisions are made, and ensure that enforcement is consistent. A common architectural weakness is distributing authorization logic in a way that becomes inconsistent across components, which creates gaps an attacker can exploit. Concrete mitigations include centralized policy enforcement points, strong separation of duties for administrative functions, and careful control of privileged operations with extra checks and monitoring. The output here might look like privileged actions must require explicit authorization checks based on role and context, and privilege boundaries must be enforced at service interfaces, which is something you can later test. Now that the 6 categories are clear, the next step in operationalizing STRIDE, S-T-R-I-D-E, is learning how to apply them systematically without getting lost. A simple approach is to take each important element in your system view and ask a small set of questions per category, rather than trying to generate a huge list of threats in one pass. For a user interface or client, spoofing questions focus on authentication and session handling, while tampering questions focus on input validation and trusted data sources. For a service interface, spoofing and elevation of privilege questions focus on how the service knows who is calling and what they are allowed to do. For a data store, tampering and information disclosure questions focus on write controls, encryption, and access boundaries. For data flows, you focus on disclosure and tampering in transit, and for the overall system, you look at denial of service and resilience patterns. The goal is not perfection. It is coverage that is good enough to surface meaningful architectural actions. When you practice this, you start seeing patterns, like how identity and authorization are involved in several categories, and how logging supports multiple categories as well. A key misconception is thinking that the mitigation must be a specific product or tool, because that causes threat modeling to drift into vendor discussions rather than architecture decisions. In an architecture context, a mitigation should usually be expressed as a design requirement or control objective that could be implemented in different ways. For example, instead of saying, use product X for authentication, you would say require strong authentication and prevent token replay, which describes what must be true. This matters because architecture is about enduring decisions and constraints, not a shopping list. Another misconception is thinking every threat needs a mitigation that prevents it completely, which leads to unrealistic designs and wasted effort. Some mitigations are about detection and response, such as monitoring for anomalous behavior, and some are about limiting blast radius through segmentation and least privilege. STRIDE, S-T-R-I-D-E, works best when you allow different types of mitigations, including preventive controls, detective controls, and recovery-oriented controls. That mindset keeps you practical and helps you choose mitigations that fit the system's reality. To make STRIDE, S-T-R-I-D-E, concrete, you also need to translate threat statements into requirements that can be validated later. A vague threat statement like, an attacker could access sensitive data, is a starting point, but it does not tell you what to build or how to verify you built it. A better version would specify the path and condition, such as an unauthenticated user could query the report endpoint and receive sensitive records because authorization is not enforced at the service boundary. From there, the requirement becomes clearer, such as all report queries must enforce authorization based on user role and data sensitivity, and responses must be filtered to only authorized records. Notice how that requirement can be tested through functional behavior without needing to know what technology implements it. This translation is one of the most important skills in making threat modeling valuable. When you can produce requirements that are specific and testable, you are no longer just naming risks, you are shaping the system. Another important step is prioritization, because a threat model that produces hundreds of items becomes hard to act on. Prioritization does not need to be complicated for beginners, but it should be intentional, and it should connect to impact and likelihood in a common-sense way. High-impact threats involve data that could seriously harm people or organizations if exposed, or actions that could cause major loss or unsafe outcomes. High-likelihood threats are those with common attack paths, weak boundaries, or exposure to untrusted inputs. Stride, STRIDE, helps you find categories of threats, but it does not automatically rank them, so you must decide which mitigations are architectural must-haves and which are improvements to consider later. A practical approach is to focus first on threats at major trust boundaries, threats involving privileged actions, and threats involving sensitive data flows. Those areas tend to produce the most valuable mitigations, and they often align with what audits and reviewers will care about as well. It is also useful to understand how mitigations can address multiple STRIDE categories at once, because that is often how good architecture works. For example, strong authentication directly helps spoofing, but it also supports repudiation by linking actions to identities, and it can reduce elevation of privilege by making privilege assignments clearer. Encryption in transit helps information disclosure and can help tampering if integrity protections are included, while secure logging helps repudiation and can assist in detecting tampering or privilege abuse. Segmentation and isolation can reduce information disclosure and limit the blast radius of elevation of privilege. When you recognize these overlaps, you can choose mitigations that give you more security value per design decision. This is not about being clever. It is about being efficient and consistent, especially when system complexity grows. A good threat model shows these relationships so the architecture looks cohesive rather than patched together. As you operationalize Stride, STRIDE, you also need to keep the scope of mitigations realistic and aligned with what architecture can control. Architecture decisions can define where trust boundaries are, where authorization is enforced, how identities are represented, and how critical data is protected. Architecture decisions can also define resiliency patterns and observability expectations, which affect denial of service and repudiation. What architecture cannot do alone is guarantee perfect user behavior, eliminate all software bugs, or make an unsafe environment safe without supporting controls. This is why mitigations often include both design constraints and assumptions, such as assuming an identity provider is trustworthy or assuming keys are managed securely by an organizational process. Being explicit about assumptions is not a weakness. It is how you prevent a threat model from becoming fantasy. If an assumption is shaky, you can elevate it into a requirement, such as requiring key management practices that meet certain integrity and access standards. To close the loop, an operational stride, STRIDE, process should leave behind artifacts that are useful to the people building and reviewing the system. At a minimum, you want a clear statement of scope, a simple representation of key components and data flows, a list of threat statements mapped to categories, and a set of mitigations written as design requirements. You also want traceability, which means you can point from a mitigation back to the threat it addresses and from that mitigation forward to where it is represented in the design. This traceability is what makes threat modeling more than a meeting. It becomes part of the design reasoning. When people later ask why the architecture includes a certain authorization boundary or a certain logging requirement, you can connect it to specific threats. That connection is persuasive because it shows the decision was not arbitrary. It also helps prevent security from being treated as an add-on, because the design is visibly shaped by the threat model from the start. By now, the idea behind Stride, STRIDE, should feel less like a memorization task and more like a method for turning security concerns into architecture choices that can be explained and tested. Each category offers a different way a system can be harmed, and your job is to apply those categories to the parts of the system where they make sense, especially at boundaries and high-value assets. The most important move is translating category labels into specific threat statements, and then translating those threat statements into mitigations written as concrete, testable requirements. When you do this well, threat modeling stops being a vague conversation and becomes a practical design discipline. It also becomes easier to communicate with others, because you can explain what risk you are addressing and what design decision reduces that risk. In the next stages of learning, you will build on this by prioritizing mitigations, validating design behaviors, and ensuring changes over time do not silently reintroduce the same STRIDE problems you worked to reduce in the first place.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.